All right, we're back with a new part 2 of chapter 18. The first video is from a few years ago and is quite lengthy and covers a lot of the setup and the whole introduction and discussion of the Fourier Transform, different from the Fourier series, of course, which was chapter 17. So now we're going to talk about the transform notation, and the first 3 sections, of course, are covered in that earlier video, point 1, but part 2 now, we're talking about circuit applications. All right, and just like with the Fourier series, we want to talk about this as just as kind of common sense. It's not like some whole new mathematics has been sprung on us or any of that sort of thing. So here's what I want to get across. We've got a term like this, the voltage, right here. The voltage is some Z, we call this an impedance, right, times I. I mean, this is really still Ohm's law, right? Nothing changed there. We do this sort of thing. But now it's in terms of frequency. That's the big deal. That's maybe a change here. It's in terms of frequency. All right, but the elements are the same. They're just the frequency versions of the resistor, the inductor, and the capacitor, right? Nothing's changed there. But except we've now moved it into the frequency domain, and that's something that's going to be, likable and tangible for the Fourier series and the Fourier transform. Fourier series is relating time domain, frequency domain kind of things. Well, now we're going to move into the frequency domain. The series itself was in the time domain, remember. Okay, so this simple form can also be written as a general form here, right? Here's just a general form of something relating. We've seen these as relationships. Ohm's law, we could say, is a special case of this general relationship. Some item y is a function of something h times x, right? This could be sales at a roadside stand for apples, given the number of apples that I had, how many sold. Okay, I mean, it could be anything. We're just talking about functions of frequency now. Okay, and what we want, the important thing here that we want to turn around to get to the transform thinking and to get to circuit applications, because I started with something that looks a lot like Ohm's law. If we just twist this little guy around and solve for h, right, as is done here, we solve for h, it's a function of one item over another, y divided by x. Okay, so it's sort of like output divided by input is the transfer function. Okay, and in fact we draw that as a little box here where the output right here is a function of the input according to this rule, h of w. But all of these are in the frequency domain. They're all frequency characteristics. Okay? So let's let me make a comment here. If we have, because this is going to relate us to the time domain, right? So y is simply equal to h of w. In other words, this will be this if somehow this is unity. Okay, this is this, so that's the same as that formula up there, if that's a unity. Okay, so how does that happen? Well, for the case of, I'll just write it out, for the case of, x of t, right, so when when x is a time function, and it is equal to the impulse response, okay, x of w is equal to 1. Okay? And then you get this. So what is this? This is the Fourier transform of simply the h of w, the transfer function in here. And I get, so this relates the Fourier transform in time to the transfer function in frequency if we take the case of applying x as the delta function, an impulse function. Okay? All right. So this by the way, this guy right here, this of course is not h of w. This is not unlike h of s, right? So this is not unlike h of s. Remember when we talked about transfer functions back in chapter 14, when for s equals jw, right? So we're really talking about the same things again and again here, okay? Okay, so to illustrate this now, I want to do one of the problems of the text, the practice problem 18.7, which isn't worked out for you there. So forget this little scribble, but this is that problem. And it asks, given a certain VI, which I believe is this, what's VO as a function of t, right? What's VO? Okay, so the first question we might have is, what is this thing? This little, where am I at here? Yeah, here, this. Whoa, the sinum. What is that sinum? Okay, well, let's take a look at it. The sinum is actually a function that's related to the unit step, except it's shifted down 1. So you could say it's -1 as an example if t is less than 0 and 1 if t is greater than 0. And I found a picture here, but forget these axes. This is basically that function. Literally, this function would go, what, from down here up to here and over. So that's the sinum. Okay, it is related to the unit step function in that the unit step function is only positive and 0 if time is negative. Okay, so the question then is, how is this circuit going to react to this sinum equation? So now we have the sinum. So we need to find out, because we're gonna do this as a transform problem, right? That's the whole point here. And what we need to find is, how is the sinum? We can go look that up in our tables. Back in our tables 18.1, we can look up the sinum, but it amounts to being the sum of a constant and the unit step, just like the picture shows. Okay, so you can grind through. I won't do it here. You can probably also look up the sinum Yes, it is 2 over j omega is the transform for sinum. And we have 5 sinum. So one thing we might want to remember here, I mean, you can work that out adding these pieces. You can work this back and forward. But the transform here is going to be 2 over j omega. We'll remember that, right? That's going to be the Fourier transform in frequency of that thing. Well, that's for the sinum. So for us, it's going to be 5 times 2 over j omega, which is 10 over j omega. Now, why do I go to all that fuss? Because this is what? V in of omega. Okay? In other words, in our example of the previous page, y equals h times x of omega. This is our x of omega. This is the input to the box, right? Now we're going to find the transfer function. So in a way, we've got here a box that sort of looks like this, right? Here's our h of w. Here's our x of w, which we now know to be 10 over j omega. And the output is going to be our y of w in that old form, and that's v out of w, right? So what is v out? Well, we don't need fancy math or anything. This is a simple circuit that we recognize as a voltage divider. That's all that's being asked for here, right? So V out of omega is going to be what? 4 over 4 plus j omega. This is simply this. The impedance here is j omega. 4 is 4 plus j omega. So this is in essence our transfer function, right? Times v in of omega. Okay, so here's our h right here. So all we have to do now is figure this. We have v in terms of omega. This is our 10 over j omega. We just now have to get this in a convenient form to be able to get our to go pick results out of a table, to unpack the thing, right? So we can we can say now that v out of omega is what? 40 over 4 plus j omega times j omega. Okay? And now from here, it's some math. We've got to get this. What we really want to get this is to the form of, in order to, and we have to get this because it makes our transformations simple to unpack. We want to get the form of something a over 4 plus j omega plus b over j omega. And if we can get it in this form, this is a very simple transform plus a very simple transform. So this is beginning to look like a Fourier transform. Okay? So how do I want to do this? I have to pick some a and b so that this works. Well, if I were to do all this and multiply this out to get it back to the form right above it, right? I would have a, this is called, getting partial fractions. A j omega over 4 plus j omega. I'm going to take that times that plus that times that, and then they go over a common denominator. So a j omega plus 4b plus b j omega. And you may have another way to do the partial fractions here, times jw, right? So this has to get to a point where this is equal to 40, 40 over these two things, right? So all we're doing is now saying this numerator has to equal 40. So A has to equal minus B, and that'll take the j omegas out of there. And 4B has to equal 40. All right, so B equals 10, and A equals minus 10. Okay, and we now have, back in our equation here, we have V out of omega is equal to minus 10 over 4 plus j omega plus 10 over j omega, right? And if we go back to our trusty tables, I think they're tables 8.18.2, and I look at the reverse of these. I now want to go back from the Fourier transform. We're looking at the Fourier transform pairs, right? I can go back and say the first one, this one here, 10 over j omega, right? This guy is back to our sinum thing. So this is like 5 sinum, something like that. 5 sinum of t. And this is 4 plus j omega. It looks to me like this is going to be e to the minus 4t u of t. So minus 10 e to the minus 4t u of t. Okay? And though it was sitting right here, I actually had all that right there. So there's our minus 10. Oops, we got something wrong with a minus sign here. On he has 10. Oh, I see. 10 times 1 minus 5 is plus 5. These two actually become plus 5. We have the same answer. Minus 4 e to the minus t, or 10 times e to the minus 4t. So we have that. We have 5. We just came at it a little bit cleaner, and then he separated. So we got the same answer they did. But key steps there, recognizing what sinum is, doing partial fractions. But otherwise, we basically just applied Ohm's law and went at it that way. Okay? So that's it for this one with a circuit application. There are other wonderful examples fully worked out in the text. I chose this one obviously because it wasn't worked out in the text, and you can get a little bit of a feel for how that goes. All right? And we'll be back with the next video.